So, okay, we just had a little bit of discussion about the composite chapter. A composite chapter is basically a combination of all the 6 chapters we have learned earlier: Newton mechanics, elasticity, and density, pressure, working energy, power, moment, and stability. All of them together. So, in one question, we have to use equation from more than one chapters. That's why they were named as composite problems. So, I want you kids to attempt these things all together, and eventually we'll solve them on a need to know basis. We have actually another type of composite worksheet, which I think would be available. I can see it find it over here. Let me just show you. No, not this one. I have a total composite. I have a compilation that's compilation number 25. That's a total composite. These 37 questions actually go across the whole syllabus. So they are not essentially within the same topic. I mean, you can have wave and work energy power together in a question. You can have some radioactivity and some moment question together in a single question. So these are the type of questions which are total composite, which means they are covered across topics. You can have a bit of thermal, and then from the thermal you can have the question about a little bit of, let's say, electricity. So these type of questions are something that we have defined as total composite. Total composite is পুরো সিলেবাসের composite. So এটাও আমরা ওই পুরো সিলেবাস শেষ হওয়ার পর এটাও তোমাদেরকে দিয়ে দেবো, লাস্ট বুকলেটের সাথে এটা থাকবে। Then we will try these things from this chapter as well. আচ্ছা, এটা না জাস্ট কম্পোজিট জিনিসটা কি সেটা নিয়ে আলাপ করলাম, so that we don't have any confusion later on. So if you are, since you are not asking many questions from the density pressure chapter, I'll start the lecture class on the thermal chapter. Because I don't have any written notes for this thing or compile note yet, so I'll start writing on the whiteboard and give you some instruction. I'm not asking you to write anything for the time being. If you have to write anything, I'll tell you what to write, and you should write at that point. For the time being, till I don't ask you to write anything, please keep observing and listen, and if you have any question, raise your hands or ask me the question so that we can interact with each other. So thermal is the second topic of our syllabus, and it's actually quite simple. The thermal chapter is simple because it's a small topic. It's not as big as Newton mechanics. Newton mechanics happens to be the biggest topic of the whole syllabus, and with my missed classes and everything, it took us a really long time. I really plan to cover it. So within the thermal chapter, so I'm just going to write the topic name: thermal physics. We have a couple of things. I can use black. First, we have the idea of thermometer and what do we mean by thermometric property. Thermometric properties. So this chapter is altogether about the thermometer stuffs, that how does the thermometer work and blah blah, different type of thermometers there are, and all of those variations about this thing. This is one first chapter. The second chapter that we have is kinetic theory of matter, kinetic model of matter. This is just a very small chapter where we discuss about the 3 different states of substances, how do they differ from each other, and also a little bit about the gas laws. We have only one formula in this chapter, that's Boyle's law, and we're going to learn to do some calculation using this formula, Boyle's law. So this is the second chapter, and we also have evaporation in this chapter. No, evaporation is not in this chapter, sorry. The third chapter that we have is heat capacity and latent heats. So this chapter actually deals with the most elaborate calculation part of this whole topic. We have heat capacity, special heat capacity, then we have give a calculation for state change and calculation for the temperature increase of an object and how much heat would be required if we have 2 different objects taking heat from a single source. For example, let's say you have a cooking pot where you have some water and you're going to heat it up, and eventually we want to boil all of this water. So to make this happen, you have to heat up this cooking pan. You also have to heat up the total water as well. So how much is the total amount of energy you're going to require? So that's basically the most type of calculation for this chapter, to calculate the amount of heat required for some process, or the amount of heat given up if some object is going downwards. In this case, I mean that going on the lower range of the temperature, either it is having a temperature decrease, or it is going from a gaseous state to liquid state, or liquid state to solid state, in which process heat has to be extracted out of the object. So those kind of calculations are involved within this chapter. And this chapter also has an important topic called evaporation. Evaporation, it doesn't have any math in it. Evaporation is altogether a theoretical concept. There are a lot of variables that we have to talk about, that what are the factors affecting evaporation, what actually happens in evaporation, why is this useful for us, and so on and so forth. And the last chapter that we have is heat transfer process. Heat transfer process. Heat transfer process basically handles the basic three type of heat transfer processes that we have: conduction, convection, and radiation. And what are the implications of this thing, of these three different mechanism? How can we? What are the differences of them as well? And also at atomic level or at molecular level, how does the medium actually affect these three processes if medium is involved? I am using this term if medium is involved because in the process of radiation, medium actually does not pose much effect. And also we have to learn about the absorption capability, or the reflecting capability or radiating capability, depending upon the surface finishes. That's for the radiation part. And also we also have a lot of practical examples within this chapter, that how a certain process of heat transfer can be useful for us, or in which cases heat transfer is not expected. For example, if you think about it, if we're cooking something, we expect a very fast heat transfer. You preferably use metal pots so that heat is transferred from the flame, whatever that flame is, to the to the food substances, uncooked food substances, pretty fast. That's why we prefer to use a metal pot. So in those cases, heat transfer is expected. And there are certain other cases where heat transfer is not expected. For example, if you are in a cold country, you are trying to keep your house warm, or if you're outside, you are trying to keep yourself warm. So you're going to put up some woolen clothes or such stuffs. So how do we prevent heat transfer in cases we want to prevent it, or how we facilitate heat transfer in cases we want to facilitate that? And there are a lot of different examples that we're going to see about in this chapter. And truth be told, heat transfer processes are involved in so many different aspects of our life that there can be hundreds of different examples that can be involved for this chapter, all of which we are not going to discuss. But I'm going to give you the core basic idea for how to analyze a certain process, how to take a bite for any given scenario, and slowly walk your way through to the end of that discussion. So I'm going to teach you that part. So discussing every single example is out of the question. It's not possible, because there can be so many different examples for heat transfer scenarios. But I'm going to teach you how to handle any question that comes within using these examples. So these are the basic core surface level content for these 4 chapters. We're going to start the thermometer chapter for today's class. And let's have a look, and let's jump directly into thermometers. So before I go into the thermometer, we have to first define the temperature scale. Temperature happens to be one of the SI base quantity, and SI unit, standard international unit for temperature, is Kelvin, not degree Celsius. But before scientist Kelvin defined his scale, the most commonly used temperature unit was degree Celsius. Degree Celsius was actually named after scientist Celsius, who did extensive work upon this. And he proposed that because water is such an abundant substance on Earth's surface, he proposed that we're going to consider the melting temperature of ice as 0 degrees Celsius, and we're going to consider the boiling temperature of pure water as 100 degrees Celsius. I'm going to get into the exact definition of melting ice point and steam point later, but I'm just giving you a bit of an idea what these scales are. So scientist Celsius proposed this, and the in-between gap would be divided in 100 equal spaces. So each of these small division is going to give us 1 degree Celsius. So that was the proposed scale for the temperature, and people used it for a really long time. We still use it because it's very convenient. Then much to experiments were done. Then there actually came a certain point where the scientists actually agreed that base units or base quantities should not be defined using a very specific substance. Base units should be reproducible at any point of the whole universe, which means if we want to define base unit of temperature in terms of kg, in terms of degrees Celsius, then we are going to require pure water in any place where we don't have access to a thermometer and we want to create this thermometer, if you want to create this thermometer from scratch, you have to have access of pure water, because it was altogether defined using pure water properties. So that to achieve that freedom or non-independence of a definitive substance, scientists then were looking for a different scale, and that's when Kelvin scale proved out to be a material which is not dependent on any substance. Scientist Kelvin actually is a pretty amazing, did a pretty nice job. His scale definition was actually derived from scientist Charles's experiments. What the Kelvin scale essentially tells us that any object, whatever, solid, liquid, or gas, doesn't matter, if you start to extract heat out of it, if you continuously keep on cooling it, there happens to be a lowest temperature beyond which it cannot be cooled any further. And that lowest temperature is the temperature which essentially uh, is the smallest possible temperature or the lowest possible temperature in the entire universe. That temperature was defined as 0 Kelvin. So the lowest possible temperature for any object in the entire universe is 0 Kelvin. And from here on, we can go further up. What within this scale, when these two scales were trying to be getting compared, what he found out, the way he defined it is that this 0 degree Celsius temperature was equivalent to 273 Kelvin. Actually, it's 273.16, but you can use 3SF values. And for the sake of easier conversion between the two scales, he determined that the boiling temperature of water or the steam point will be defined as 373 Kelvin, so that the gap over here is still 100 Kelvin. And over here, the gap was 100 degrees Celsius. So this actually brings us to a pretty nice idea that delta 1 degree Celsius is equal to delta 1 Kelvin. 1 degree Celsius temperature increase means 1 Kelvin temperature increase, and vice versa. However, 1 degree Celsius is not equals to 1 Kelvin. You have to understand that 0 degree Celsius is 273 Kelvin, which means 1 degree Celsius should be 273 plus 1 Kelvin, which is 274. So 50 degrees Celsius should be 273. If I write 50 degrees Celsius over here, this is 273 plus 50 Kelvin. So like that. So if you want to convert the degree Celsius value into Kelvin value, we have to add 273 to it, and vice versa. If you want to convert a Kelvin temperature into theta degree Celsius value, we have to subtract 273. There is a very basic formula in terms of variable that I can show you, that if you are trying to define two different temperatures, let's say theta degree Celsius and T Kelvin, then we can write that theta equals to T minus 273 degrees Celsius, or we can write T equals to theta plus 273 Kelvin. So these are two equations that can help us to achieve the value or the conversion between the two scales. এই পর্যন্ত বুঝা গেছে কিনা বলবান? কার কোনো কোশ্চেন? আচ্ছা, if you have any question, we're going to pick up those questions right after the Maghrib prayer. It's 5:50 right now.
ওইটার জন্য হ্যান্ড রেজ করেছি
right now. So we're going to take 10 minutes. So we're going to resume class exactly at 6:00. Break. We resume the recording. So this is the idea about the temperature scale and degree Celsius scale. We are going to use either of these scales for both of our calculations, because for most of the cases we don't have to use the absolute value of temperature. In most cases we have to use the temperature difference for all the calculations involved in our O-level syllabus. So we are going to work with delta theta or delta T. So for both of these cases, the value would be exactly same. Numerical value would be exactly same. That's why I wrote this information. Have a look. 1 degree Celsius temperature difference is the same as 1 Kelvin temperature difference, but 1 degree Celsius itself is not equal to 1 Kelvin. So এই আইডিয়াটা বুঝা গেছে কিনা? Is this clear to all of us properly?
জি স্যার.
Okay, the next thing that we have within this chapter is what we call thermometers. Now, what are thermometers? Thermometers are physical devices which can measure the temperature of an object. It's very basic. How do we measure the temperature of an object? Now, this is a very important question that you need to understand. What is the expression of temperature for an object? Any object above 0 Kelvin has some internal energy within this object that can be extracted. I'm using a lot of words over here. I'm going to go through each of these words one by one. Any object that is above 0 Kelvin has some internal energy within itself that can be extracted out. So if an object is at 0 Kelvin, then it will also have internal energy, but that energy cannot be extracted out. If an object is above 0 Kelvin, we can extract out that energy, and it is that extractable energy that we call the heat energy of the object. The way any object stores heat energy within itself is by means of motion of its particles. The term motion is very important. Motion in this case can either mean vibration. Motion can also mean translation. Translation means physical movement from location A to location B, whereas vibration means having a back and forward and backward or to and fro motion about the same equilibrium position, or what we call mean position. So both of these, in both of these motion behavior, an object can store energy. Now, to understand the idea of this stored energy better, we need to discuss the basic structure of substances. So this part that I'm about to discuss for the structure of substances will actually fall within this kinetic model of matter chapter. So this is a bit this is not essentially within this chapter. This discussion that I'm about to do belongs to this chapter, which is perfectly all right because the thermal chapter is somewhat intermingled. So just hear me out. Solid substances are such that its particles, we use the term particle in a lot of cases because the word particle can simultaneously mean atoms or molecules, wherever it is applicable in the way that we're using. So if we are considering an element, particles would mean atoms. If you're considering a compound, particles would mean molecules. If you consider the gaseous state of a certain element, for example, let's say if you consider, let's say, mercury vapor. Mercury is a very special metal which is a liquid at room temperature. So if we produce very low pressure on the open surface of a mercury amount, which we have seen for the barometer case, then certain atoms of mercury can become evaporated. These atoms will not coalesce together, or they will not get joined together to produce a molecule. Even in the vapor state, they will maintain their atom level. So each atom would be individually separated. However, that's not the case for the typical other gases that we know about. For example, if you think for nitrogen or oxygen or what other gases are there? You name it. So typically those gases actually produce a biatomic molecule. Then again, with the exclusion of helium. Helium being a noble gas, it also maintains itself in atomic state. So what I'm trying to tell you over here is that depending upon the internal chemistry of the molecules or atoms, a free existing entity could be an atom. It could also be molecule. So that's why, to avoid confusion, we usually use the term particle, because particle can mean either of them whenever it is applicable the way it is supposed to be applicable. So I'm going to use the term particle. So you can think in particle term. If you're thinking of some biatomic gas, you think it as the molecule of that gas. If you're thinking of some metal, you think about a single atom. Okay. The way a solid substance is arranged is that its particles are fixed in a three-dimensional space. They are incapable of moving away from that location. They're practically stuck there, and all that they can do is they vibrate. If we increase the temperature of a solid object, that vibration will increase. Now, whenever I use the term vibration will increase, what do I mean? Increased vibration can have two aspects of it. Try to think about a particle that is vibrating. So try to visualize an object is moving left and right. Try to visualize it. Vibration increase can have two aspects. First aspect is that we can have an amplitude increase of the vibration, which means, let's say the particle was earlier moving within a space of 2 centimeter with an amplitude of 1 centimeter. So let's say from the equilibrium to one of the extreme side, the length is, let's say, 1 centimeter. So the total movement space was 2 centimeters. So that's the total amount of movement that the particle is doing within a space of 2 centimeter length. If you increase the amplitude, then the particle is going to cover longer space between the motion. So a particle can have increased amplitude whenever its vibration increases, whenever you see the words vibration increases, and /or, which means the second thing can be frequency increase, which means the particle can have increased number of vibrations per second. For example, let's say at a lower temperature, maybe a certain particle is doing 100 vibrations per second. At a certain high temperature, it can do 120 vibrations per second. Maybe the amplitude will remain same, or maybe the amplitude will increase. So these are the two factors which control the term, or which imply the output of the term or the phrase vibration increases. It could either mean amplitude increase and slash or it could mean frequency increase. And slash or means that either of these happening can happen individually, or they can also happen simultaneously. So within a solid substance, the particles are practically all stuck within their original position, and they cannot move around. They cannot move around, and they actually have to be steady at this position, and all that they can do is vibrate. This vibration gives the solid substance its kinetic, its heat energy stored. If we start to reduce the temperature of a solid object, it's gonna slowly start to experience reduced vibration. And that reduction is possible to make happen all the way up to 0 Kelvin. Whenever the temperature of the solid object reaches 0 Kelvin, it no longer has any vibration available, which means what I want you to visualize, try to visualize a solid object with multiple particles. They're all vibrating, they're all moving around a little bit. And if you start to reduce the temperature of this object, the vibration will reduce, and at 0 Kelvin, all the particles will become standstill. They are not going to move, they're not going to vibrate, they're going to become standstill in their position. So that's the significance of 0 Kelvin. It means at that position you cannot extract any further energy out of this object. So that's the basic definition of for 0 Kelvin. So এটা হচ্ছে solid substances behavior. Within the liquid substance, particles are not stuck in a fixed position. They can move around each other, they can slide past over each other, but they're still in contact with each other. So so they're still in contact with each other means the particles are pretty much like, what can I say, like মুড়ির টিন। বলো মুড়ির টিন বুঝো?
Yes, sir.
মুড়ির টিন মানে হচ্ছে যে, let's say you have a container where you have put some puff rice. Okay, exactly. So if you just roll this container, those particles of food or those grains of puff rice, they're gonna move around. So liquids are like that. Whereas if you make moa is one of these local mishti where we use some crude sugar to mix up with the puff rice and make it into a bowl, which is pretty tasty to eat if you have had it. That is sort of like a representation for the solid objects, where the individual grains of the puff rice, they are pretty much stuck within that structure because of the crude sugar. They are actually, that is working as a glue, so the particles cannot move around. But whenever we haven't used that, the puff rice is all together within a container. If you roll the container, the puff rice are going to roll over each other and move past each other. That's sort of like the situation for the liquid substance. Does this example resonate with you? Can you visualize this thing properly, everyone?
Yes, sir.
এটা বুঝে গেছে সবার? কার কোনো কনফিউশন?
No, sir.
Yeah.
আচ্ছা, so এটা হচ্ছে এই সিচুয়েশন, and so what the reason I'm giving you this example is to give you a bit of an idea that the average intermolecular space or average intermolecular distance between two particles of a solid object and two particles of a liquid object is pretty much same. The average intermolecular distance between the particles of a solid object or a liquid object are pretty much same. They are not so different. The only difference that they have is that within the solid object, the particles cannot move around, they're stuck. The only thing that they can do is vibration. And within a liquid object, the particles can move around. So interesting enough for you to understand that within the liquid particles, because they are actually stuck, actually touching each other, the liquid particles do both of the motions. The liquid particles can vibrate. If you wonder why would they vibrate, the reason they would vibrate, because let's say try to visualize a liquid object, a liquid that is made up of a lot of particles. If you give energy to one of these particles precisely, that particle is going to start to move. But can it move freely? It is surrounded by the other particles. So the moment it starts to move, or it attempts to move, it will collide with one of the other particles and eventually bounce back by Newton's third law. and then it will hit another of this particle and it will bounce forward by Newton's third law. So the vibration motion or back and forth motion is inherent, but within this vibration motion they can also cover physical space depending upon the density difference. So for example, what happens in the convection process of heat transfer, which we're going to see in the heat transfer process in more detail. The idea of convection process, just I'm giving an example to make sense with you. Whenever the convection happens within a liquid body or within a fluid body, the location of the fluid that is hot, that at that location, at that specified location, the intermolecular space increases comparatively more comparatively more than the fluid that is around. So that location becomes less dense and it becomes lighter, and that because of the density difference, the hot fluid that can be liquid or gas, that hot fluid starts to go up, and to fill up that left space, that void that the hot fluid is leaving, cold fluid comes in to that place, and that's how the whole convection current, the hot current, the cold current works up. Now, why am I telling you this? I want you to understand that the average intermolecular spacing between solid particles and liquid particles are quite same. The only difference between them is that within the solid, the particles are practically all stuck in their position, and within the liquid, the particles can move around. They have the capability to move around. What happens in the gas? Within the gaseous substance, particles are absolutely free of each other's attraction. The concept of ideal gas that we have in our syllabus, and whenever we define something as ideal in physics, please listen to this thing very carefully. Whenever we define anything as an ideal equipment or ideal concept, it means that it is non-existent. It does not exist. It is a highly simplified version of a pretty complicated example or pretty complicated scenario. For example, if we consider the scenario for ideal gas, ideal gas says particles are considered to have no forces across among each other, no forces, and this no is a big no. They have no forces among each other except for whenever they are in collision. So it means that as the moment that two particles will be colliding with each other, physical collision, they will actually bump into each other. Only at that point they will exert forces on each other by Newton's third law. But before that, no matter how close or how far they are, they will not exert any force onto each other, which if you think is highly unlikely because particles have masses. So if you even forget about all the other type of forces, electromagnetic forces, van der Waals force, if you forget everything, they definitely do attract each other because of gravitational force, because everything that has mass is subjected to gravitational force. But the concept of ideal gas actually covers that no ideal gas particles have no force within each other unless when they are colliding with each other or with the container wall. That's the only case they are going to experience any force. And there are a lot of other stuffs of other assumptions for what is postulates for the ideal gas theory, which are all unrealistic. The reason we deal with this unrealistic situation is because we want to teach you a very simplified version of a new thing, and then slowly we want to introduce the complexity within this part. Does it make sense? Palawan. The point I'm trying to make, that if you ever come across something that is called ideal, you have to understand that it is highly simplified and definitely not practical. Another of this thing which I usually say at this part of the lecture to the other kids, not part of the heat chapter, is that there is a thing called simple pendulum in physics. The definition of simple pendulum is not simple. I'll tell you the definition of simple pendulum, and I want you to visualize this thing if you can. The definition of simple pendulum goes like this. If a particle with mass is suspended using a weightless, inextensible, flexible string. I'll go again. If a particle with mass is suspended using a weightless, inextensible, flexible string, and it can oscillate only under the effect of gravitational force. It can oscillate only under the effect of gravitational force. This setup is called a simple pendulum. Can you kids think of a logical way to create this simple pendulum on an earthly environment? Try to imagine.
Sir?
The first thing that we're saying that a particle or with mass. Now, what do we understand by the term particle? What is the definition for a particle? Can someone help me remember? I told you earlier.
স্যার
What is
আপনার
it?
আপনার স্ক্রিন হ্যাং হয়ে আছে স্যার।
না, আমি স্ক্রিনে কিছু করতেছি না, আমি জাস্ট কথা বলতেছি, ওই জন্য স্ক্রিন হ্যাং হয়ে আছে।
আচ্ছা
আমি জাস্ট কথা বলতেছি, যখন লেখার সময় হবে তখন আমি লিখবো। I'm trying to make sense with you with some lecture. So can anybody recall the definition of a particle? What is a particle?
Particle is the amount of substance present in a body.
That is not particle.
Isn't that mass?
That would be mass, I think. Yes. Okay, I'll tell you the definition for particle, and hear me out and try to visualize it. A particle is an object that has mass but zero volume. I'll say it again. A particle is an object that has mass, small or more, doesn't matter. It has some mass, but it has zero volume. Now, can you visualize it?
Yes.
Can you, in your imagination, see an object that has zero volume?
No.
No.
None of us can. We cannot even imagine a point, because a point is also that same thing, which doesn't have any dimension. It only has existence. It's basically a coordinate. It's basically a location. The moment it has dimension, it becomes something else. It can become an ellipse, it can become a square, it can become a square, it can become something of geometric figure. So similarly, a particle is defined to be something that has mass, but it has zero volume. So the first point of simple pendulum, that when a particle is suspended, when a particle with mass is suspended, which means we cannot achieve particle in regular life. So that is the first unavailability of the whole definition. That's point one. Then the definition of simple pendulum goes like this. When a particle with mass is suspended with a weightless, inextensible, flexible string. So you are trying to achieve a string that would not have any weight, which is also impossible to achieve. It has to be inextensible. Inextensible means no matter how much force you apply on it, it will not bulge. It will not undergo any type of deformation. No matter how much force you apply on it, it will not extend. That's what it means by inextensible. So a weightless, inextensible, and flexible. So it has to have some sort of flexibility so that it can allow the free movement of the particle. So if we hang it in this situation, and then the particle can oscillate only under the effect of gravity, which means the effect of air resistance or the effect of any other forces involved in the nature. All of those forces have to be absent altogether. I mean, achieving zero air resistance is not impossible. We can achieve it by producing vacuum. Vacuum with a vacuum pump, strong enough vacuum pump can do that. But if we say that it will be only subject to gravitational force, making sure that it is only subject to gravitational force is actually quite a hassle. So that's the idea of that's the idea that we entertain in physics, that is defined as ideal. Whenever something is defined as ideal, it means it is highly simplified compared to what is realistic of that version. So ideal gas is also something like that, which doesn't exist in nature. We just use the concept of ideal gas to make better sense of how the complexity is gonna be added to the same situation. Now, the reason I was talking about ideal gas is that the way gas particles, the way the state of gas or the structure of gas is defined is that the particles of a gas are absolutely free of each other. There is no attraction between them, between the gas molecules or the gas particles, except for when they are in collision. The collision can be of two types. They can have collision with each other, or they can have collision with the container wall as well. And in the gaseous state, the particles have huge intermolecular spacing, because gases don't have any fixed shape or volume. They don't have neither of that. So whatever the container that you put them in, they're going to occupy the entire volume of it. So if you push them from a small container into a large container, they're going to have increased intermolecular spacing. If you push them from a large container into a small container and that thing still remains gas, they're going to have a smaller intermolecular spacing. So, and the only type of motion gas particles have is kinetic energy. And the only type of motion the gas particles have is translation, which means physical movement from point A to point B. They don't have vibration because they are not touching anything, so there is no question of having vibration. Excuse me for a minute. So yeah, so that's the whole idea for the gaseous substances, that the only type of motion they can do is translation, which means they can move from point A to point B. In this case, what I mean by point A to point B is that in between collisions, they're gonna cover distance in straight lines, and whenever they collide with something, either with another gas particle or with the container wall, they're gonna bump into that and get reflected to another direction, and that's the only type of motion they can have. So gaseous particles don't have vibration. So to summarize, solid particles are stuck in a fixed position. All that they can do is vibration. If we increase the temperature, their vibration can increase. Increased vibration can have two aspects. It can happen by increased amplitude of vibration and/or increased frequency of vibration. Liquid particles are not can move around from one point to another point. They are not stuck with each other, but they are still pretty much touching each other. So liquid particles have pretty much the same average intermolecular separation or distance as the solid particles. Liquid particles can have both vibration and translation type of motion, and they don't have any fixed shape, but they have a fixed volume. Whereas solid objects have fixed shape and volume both. And for the gaseous substances are absolutely free from each other. Gaseous particles are absolutely free from each other. They only have translation kind of motion. So they only change their direction of movement, or they slow down or speed up, or they only change their velocity whenever they do some collision with another gas particle or with the container wall. They don't have fixed shape or fixed volume. এই পর্যন্ত কোনো কোশ্চেন আছে কিনা কারো? Anyone? Hello?
No, sir.
আচ্ছা, so এই কথাগুলি বলার কারণ হচ্ছে because I'm going to get into the whole idea for thermometer. So what I was saying, the thermometer is a device which can be used to measure the temperature of an object. The true way or the direct way to measure the temperature of an object, the true way or the direct way of it to measure the temperature of an object would be to measure the kinetic energy of each individual particles that make up the object, and have some mathematical process to convert that energy information, internal energy information, into temperature. That would be a direct method. Do you guys understand the difference between a direct way of measurement and an indirect way of measurement? Do you understand this aspect, this concept? Anyone?
No, sir.
Okay,
No, sir.
I'll tell you. A direct way of measurement is something that you measure exactly that thing using the properties of that thing involved. Whereas an indirect measurement is that you measure something else, and somehow with the idea of equivalence or with the idea of ratio, you find out the other thing. Let me put up an example. Let's say you have in front of you, you are sitting on a table. If you want to measure the length of the table, you bring up a meter rule and actually measure from one end of the table to the other end of the table. That's what you do. This is a direct measurement. You actually measure the table. Now, what if you want to measure another length, which is the height of Mount Everest or any other hill? If you want to measure the height of Mount Everest, how do you measure that? Do you drill a hole from the top of the mountain Everest and drill all the way to the sea surface and then drop some meter rule or some measuring tape through that hole to measure how deep it goes? Do we measure it that way? I mean, is it possible or is it logical? Absolutely not. The way we measure the height of a mountain is something like this. This is the sea level, and somewhere over far away from the sea. So I'm going to give a break sign over here. Let's say this is the Mount Everest. Okay, so we want to measure how high is this steep, and these two places are pretty far away. So we know exactly what is the air pressure at sea level. So whenever we are trying to measure this thing, we're going to find out a valley or flat space over here, and we're going to use a barometer, use a very precise barometer to get to the height which would give us the exact same pressure that we should get on the sea surface. That will tell us that we are now at sea level. So let's say this is that sea level over here. And then let me elaborate, let me zoom in this figure a little bit. Let's say this is the mountain, and this is the other places of mountain, and people found out that, well, this is the location where we have sea level. So what they're going to do, they're going to produce a perfectly flat platform over here, either by stacking some poles and everything. There is a horizontal surface over here, and they're going to place a viewing camera at this location. Let me zoom in. Acha, mouse wheel দিয়ে zoom করতে হবে. So they're going to place a camera over here, or a viewing a telescope over here, and they're going to place a certain length of height over here, and they're going to try to see through this hole so that the height of this pole is perfectly matched with the peak of this mountain. So basically what we are doing, let me use a different color. So basically what we're doing, that we are producing two similar triangles. Do you understand what this is? Do you see that similar triangle? So we have one large triangle over here, and we have a small triangle right over here. এই দুটো ট্রায়াঙ্গেলের এই অ্যাঙ্গেলটা এক্স্যাক্টলি সেম হবে না? This angle for the red triangle and for the green triangle should be same, right? And we can very easily measure either this green side or this height or this distance. These things are very easy for us to measure. So what the people do, that they measure this height, and then by telescopic distance they measure this hypotenuse from the peak of this mountain to this point, and then they use trigonometry to calculate how much is this. No one actually goes down through a hole from the peak of the mountain to the very base of the mountain to actually hold a meter rule or measuring tape to measure the actual height of the mountain. That no one does. We measure it by doing some other mechanism. So this is a mechanism of indirect measurement. Do you understand my point? Example বুঝা গেছে কি?
Yes, sir.
Yes,
স্যার
sir.
পোল পার্টটা আবার বুঝতে পারবেন?
কোনটা?
The pole part.
Oh, this is the pole part is very simple. I mean, actually, let me just draw a bit bigger. Let's say this is a flat surface. They're gonna put a telescope over here. They're gonna put a pole over here, and the height of this pole can be varied. They're gonna make this pole go up and down, and they're gonna keep looking from this telescope in such a way so that this pole perfectly matches the peak of the mountain to this telescope. So let's say this is the height of the pole. So now if you have a look, that we can actually have two triangles, two right angle triangles, one over here and one that is made right over here.
How do they find the height of the hypotenuse with the telescope?
Oh, that can be measured using a laser gauge. You can put one of this thing over here, and you can measure and you can put a reflector over here. You can measure it by a laser gauge.
Now I get it, sir.
আচ্ছা, সো এটা হচ্ছে ইনডিরেক্ট মেথড। যেমন এরকম ইনডিরেক্ট মেথডের আরেকটা এক্সাম্পল হচ্ছে যে মনে করো let's say whenever we use the barometer in the earlier chapter a couple of days back, in the barometer to measure the atmospheric pressure, did we actually measure the pressure under the atmosphere, or did we measure the pressure under the mercury column? What did we measure? Exactly what did we measure? Did we measure? Think, for the barometer, what is the height that we actually measure? Did we measure the height of the mercury column, or did we actually measure the height of the atmosphere? No one remembers barometer, right?
So only the height of the mercury.
Thank you.
Mercury column, sir.
We measured the height of the mercury column. We did not measure the height of the whole atmosphere. So technically, we actually measured what was the pressure underneath the mercury column, and by law or by understanding or by concept, by reason, we knew that this pressure under the mercury column is exactly equal to the pressure of the atmosphere. So we actually measured the pressure under the mercury column and equated that equals to that to the atmospheric pressure. This is also an indirect measurement. We did not actually measure the pressure under a true atmosphere. We actually measured the pressure under a mercury column. This is an indirect measurement. বুঝা যাচ্ছে? সো ব্যারোমিটার দিয়ে যখন আমরা হাইট মেজার করলাম তখন আমরা হাইট মেজার করছি হচ্ছে মার্কারি কলামে, ওখান থেকে প্রেসার ক্যালকুলেট করছি, ওই প্রেসারটাই হচ্ছে অ্যাটমসফিয়ারিক প্রেসার। ইন দিস কেস বোথ অফ দেম আর ইকুয়াল। ইন দিস and for this case we are actually measuring this one, and by using the same angle we calculated how much is this one. So there is a ratio between them in terms of trigonometric similar triangles. So the reason I'm telling you this difference, because in many cases we have to take help of indirect measurement, because for many measurement variables, measuring directly is not a very good idea, or it's not easy to do, and in some cases it can prove to be impossible as well. I mean, think about it. Let's say you have an object over here. Let's say we have a solid object of irregular shape. Irregular or regular shape doesn't matter. Let's say this object is made up of, let's say, 3 billion particles. If we want to measure the temperature of this object directly, we would have to measure the individual kinetic energy of all of those 3 billion particles, add them up together to get a total value of kinetic energy of those particles, and through some mathematical procedure or through some algorithm, we have to convert that kinetic energy information into temperature. That is essentially very impossible to achieve. So what we do, we take help of some other physical properties of objects that those are easy to measure, and those are directly proportional to the change of temperature. So let's say these properties of substances are called thermometric properties. The word is like this. Thermometric properties মানে উপরে লিখছিলাম আমি। Here is the spelling. Thermometric properties. Thermometric properties are those things. Thermometric properties, proportional language T is হবে. Thermometric properties. Thermometric properties are those properties of an object that can be liquid, that can be a gas, that can be a solid, doesn't matter. A thermometric property is such a property that changes proportionally with the change of temperature, which means if X is the symbol of a thermometric property, that this X could be a volume, this X could be a length, this X could be resistance, this X could be EMF, this X could be amar matha, this X could be tomar matha, doesn't matter. X is a variable that undergoes proportional change with the change of temperature, which means change of X, delta X, is directly proportional to change of theta. এই বিহেভিয়ারটা যেই এই প্রপোর্শনালিটা কোন একটা সার্টেন অবজেক্টের যেই ফিজিক্যাল প্রপার্টিগুলো এই প্রপোর্শনালিটা মেইনটেইন করে, we can use those properties to measure temperature indirectly. For example, the volume of a liquid, volume of most liquid, not all, volume of most liquid undergoes uniform expansion over temperature increase. So for liquids, for quite a good number of liquids, we can use this relationship that delta V is proportional to delta theta, which means volume of a liquid, change of volume of a liquid can be used as a thermometric property. If we can measure the volume of a liquid precisely, we can convert that information into change of temperature as well. So that helps us to measure temperature. In some other way, we can also convert this volume into a length, because try to think about it. If we have a cylindrical object, let's say a liquid is kept into a fixed cylinder, into a cylinder of fixed cross-sectional area. Let's say this is a cylinder and this is the liquid. So the entire cross-sectional area is uniform, which means A is a constant. If you heat up the liquid, it's going to increase in volume. Now, because it has to rise through this hollow chamber, whenever it will increase in volume, the only variable that will change is its height. Wouldn't you agree? Because this liquid cannot expand laterally. This liquid can only expand in the upward direction, which means in this case, because the cross-sectional area is constant, and we can write that volume is equals to cross-sectional area into height for any object that is true. So because A is a constant, so we can basically convert this into proportionality. So V is proportional to H. So delta V is proportional to delta H. And because delta V is proportional to delta theta, so we can also write that the change of height is also proportional to delta theta. And this is basically how we measure the temperature of any object using a thermometer, typical thermometer that we know. Try to think about it. If we use a thermometer, within the thermometer there is a liquid that goes up and down or left and right, and all that we look is how long has it gone on a graduated scale. How long has it gone? So what do we measure? Do we actually observe volume change, or do we actually observe length change of the liquid? What do you observe? Which variable do you observe? within a thermometer. As the liquid goes to
Length change.
high temperature, we actually observe the length change. So what have we done? Keeping the cross-section area constant, we reduced our effort. So measuring a volume can prove to be difficult, so we kept the cross-section area constant, so the volume measurement become proportional to the height measurement, and then that height measurement can give us the temperature information, and that's basically how we use liquid in glass thermometers. এই কনসেপ্টটা বুঝে গেছে কিনা বলবান?
Yes, sir.
ঠিক আছে, এরকম আরো অনেক প্রপার্টি থাকতে পারে। there can be a lot of other properties. For example, if you think for the pressure of a gas, volume of a gas, resistance of a certain type of resistors, EMF produced in thermocouples, and there can be also the radiation received from a certain hot object, that's called pyrometry. So there are a lot of different ways to measure temperature, but the bottom line is we can only use those properties to measure temperature which has linear variation with temperature change. যদি লিনিয়ার ভ্যারিয়েশন হয় তাহলে আমাদের এই ইকুয়েশনটা এই প্রপোর্শনালিটি কাজ করবে, এবং এই প্রপোর্শনালিটি কাজ করলে তখন আমরা এটা নিয়ে ইকুয়েশন বানাতে পারবো। সো এই পর্যন্ত যদি আমরা বুঝি, তাহলে আমরা আমি ফার্দার আবার আমার অরিজিনাল ইকুয়েশনটাতে ব্যাক যাই। অরিজিনাল ইকুয়েশনটা ছিল হচ্ছে x প্রপোর্শনাল টু v। এটা কোথায় লিখছিলাম জানো? এই যে ডেল্টা x প্রপোর্শনাল টু ডেল্টা থিটা। সো যদি আমরা এখন একটা মার্কারি কলমের জন্য চিন্তা করি, ফর এক্সাম্পল লেটস সে let me draw a thermometer. I hope to draw a good thermometer. Be good. I'm so bad at drawing straight lines. Why did I bother? I could have copied and pasted one image from the internet. যাই হোক, আঁকছি যখন আগে ফেলছি। এটা হচ্ছে টিপিক্যালি একটা এমটি থার্মোমিটারের ভিউ। মনে করো হচ্ছে এই থার্মোমিটারের ভিতরে আমরা এইটু হচ্ছে আমাদের লিকুইড। সো দিস পার্ট অফ দ্য থার্মোমিটার ইজ কল্ড দ্য বাল্ব, দিস পার্ট অফ দ্য থার্মোমিটার ইজ কল্ড দ্য স্টেম। In clinical thermometer there exists a thing over here that is called a constriction. Constrictionটা কি জিনিস, কিভাবে কাজ করে সেটা একটু পরে বুঝাবো, don't worry. And this is the stem. This is made up of thick glass, so it's not supposed to break, where this is made up with thin glass walls so that heat exchange can be made easily. So that heat can enter into this thing or it can go out of this thing pretty easily, so that the thermometer can give us the reading pretty fast, because if we use the thick wall then it would take significantly long time for the thermometer to respond. Anyway, so this is how the thermometer works. এখন জিনিসটা হচ্ছে যে মনে করো, try to understand, let's say at a certain temperature of 0 degrees Celsius the mercury was up to here. I'm now switching to the word mercury other than using the term liquid so that we can have a bit better visualization. So let's say whenever we put this whole thing within crushed ice at under one atmospheric pressure, this is the height of the mercury. So we're going to give a mark over here, and then we're going to take this thermometer and put it into boiling steam. So there are two different figures for this. Let me just find this for you. Yeah, this is the figure that I'm talking about. Or this is the actual figure that you have in your federal book. Might as well copy this one. So have a look. Using this setup like this, well, you have to understand that all of these things are essentially not floating in air. There has to be a proper support system. For example, the funnel has to be placed on a ring type of holder, and the thermometer has to be held by a clamp so that none of this fall off over. So we actually keep the thermometer in a crushed melting ice, pure water ice. And the reason we use a funnel, because so that whenever the water melts over here, that those liquid waters can drip out, making sure that the thermometer bulb is always in contact with ice and ice only. So we do that, and the mercury level is going to go down, and eventually at one point it will not go down any further. Whenever it doesn't go any further, we say that the temperature of the mercury inside the thermometer and the temperature of the pure melting ice, they are both equal. This is a situation that we call thermal equilibrium. Thermal equilibrium means whenever two objects has the same temperature, we call them to be in thermal equilibrium. The duration of heat flow always depends on temperature. It doesn't depend upon the amount of heat that an object stores. The duration of heat flow, the duration of heat energy flow always depends on temperature. Heat will always flow from hot objects to cold objects, period. Heat will always flow from hot objects to cold objects, always, without exception. And they will flow up till the point the equilibrium is reached, which means if you keep one hot object in contact with a cold object, the hot object is going to start to give its heat energy to the cold object. As a result, the temperature of the hot object is going to go down, the temperature of the cold object is going to go up, and this will keep on happening till both of the temperature becomes exactly equal to each other. So at that point, we say that the two objects are in thermal equilibrium, which means they basically have the same temperature. Or you can also say that they are not exchanging any heat across each other. There is no resultant heat exchange. Or you can also say that the heat exchange that is happening on either direction is equal. Something like reversible reaction. Did you guys come across reversible reaction in your chemistry yet? Hello?
Not yet, sir.
Not yet. Okay, fine. You will eventually get there. So that's the point that the define as equilibrium. So this is how we may use. So we may define the 0 degrees Celsius temperature on a non-calibrated thermometer by this method. To find out the steam point is the boiling temperature of pure water under 1 atmospheric pressure. This 1 atmospheric pressure is very important because pressure can have a very significant effect on the boiling temperature of a liquid, because the substance that is getting out from the liquid is gas, and gases are highly susceptible to highly affected by the pressure variation on them. So here's the definition for ice point. Hear me out. The melting temperature of pure ice under 1 atmospheric pressure is ice point. I'll go again. The melting temperature of pure ice under 1 atmospheric pressure is the ice point. And the steam point is that steam point is defined in the same way. The boiling temperature of pure water under 1 atmospheric pressure is called the steam point. To determine the steam point, what we are doing over here, we are keeping the thermometer. Have a look at the center figure 14.2. To achieve a perfect calibration of the steam point, we keep this thermometer in boiling steam. Have a look. This thermometer bulb is not kept in the boiling water. Do you see that there is a gap between the water surface and the bulb? The thermometer bulb is actually kept on the steam that is continuously being boiled up from the underneath water. It is not kept in the water, and that's the standard. So we're going to keep it in the steam, and also we have to make sure that the pressure produced is exactly 1 atmospheric pressure. To observe that pressure variation, we have kept a manometer over here. Do you see that manometer? Blowan, manometer দেখা যাচ্ছে?
জি স্যার।
এই manometer purpose হচ্ছে যে, I mean, here's the deal. Why do we have to go through such a complicated structure? Here's the deal. If we do not have a cover, you can see over here. Yeah, double was. Samira, boltesi. Have a look. This is our first. This is our inside container. So this rectangle and going all the way up over here. This is our inside container. If you don't have the cover, and if you start boiling the steam, what will happen? The steam will essentially produce over here, and because it is lighter than air, because it is pretty hot, this is simply going to start blowing out. All the steam is going to go to the atmosphere, and practically you can never have the actual mercury within this thermometer to reach 100 degrees Celsius, because the steam would not be present there to have 100 degrees Celsius temperature rise for the mercury in the glass. To achieve the 100 degrees Celsius rise of the mercury, we have to trap the steam over here. We have to keep the steam over here in contact of the mercury, in contact of the thermometer, so that the mercury can actually reach to the temperature of that steam. This is why we need a cover. So that's why we have this whole second layer cover. This is the cover. And the way this cover has to be maintained is that because we are continuously providing heat, so there is continuously boiling water, so steam is continuously being produced. So if we do not allow this steam to escape at all, this is going to work like a pressure cooker. where boiling is happening, but the gases are not coming out. So in that case, inside pressure would become higher than the atmospheric pressure. So in that case, this level should become low and this level should become higher, representing that inside the whole setup, inside all of this contraption, the pressure is higher than atmospheric pressure, and that will not enable us to measure that actual steam point, because by definition, steam point is that melting is the boiling temperature of pure water under 1 atmospheric pressure. You have to make sure that this steam that is kept trapped within this whole setup must be maintained at exactly 1 atmospheric pressure. That's where the manometer comes in. Now you might wonder, well, manometer gives us a view that whether the pressure inside is more than 1 atmospheric pressure or equal to 1 atmospheric pressure or less than 1 atmospheric pressure. Okay, I understand that. Whenever the two liquid levels of the mercury of the manometer on both sides would become exactly at the same level, then we can say that the pressure inside is exactly equal to the pressure outside, which makes sense that inside the pressure is exactly 1 atmospheric pressure. But how do we achieve that? I mean, is it going to work out for any setup? The answer is a solid no. It is exclusively or it is solely dependent upon how big is this exit hole. I mean, what is the rate of steam getting out, and also how fiercely you are hitting the bottom. Now have a look. If you apply too much heat and this steam exit pipe is actually quite small, diameter is quite small, you will be producing steam at a rate higher than the leaving steam. So inside steam would become more and more trapped, which will increase your pressure. বুঝছো কি বলতেছি বলবান?
জি
আমি যে
স্যার।
হিটটা দিচ্ছি সেই হিটটা যদি অতটুকু ফিয়ার্স হয় যে যতটুকু স্টিম আমি পার সেকেন্ডে প্রডিউস করতেছি ওই চিকন পাইপ দিয়ে পার সেকেন্ডে অতটুকু স্টিম বের হয়ে যেতে পারতেছে না, তাহলে ভেতরে আমার স্টিম অ্যাকুমুলেট হওয়া শুরু করবে, আমার ভেতরে প্রেসার বেড়ে যাবে। Alternately, if I apply too less of heat at the bottom and the pipe is pretty open, in that case, if I apply too much less heat, the temperature of the water will not be high enough to become boiled. To achieve this whole to achieve this whole to achieve this whole thing, we have to keep the steam within this contraption, and also the water has to be keep on boiling. Water has to be in a boiling state, so that's a continuous tense. Water has to be keep on boiling. So the way we actually achieve this is by taking a heater, and we actually control the height of the heater underneath the bottom of this rectangular container, and we determine that how much heat are we providing. So if you bring the heater too close to the container, you'll be heating it at a much higher rate, fierce heating. If you take the heater far away, you can do this, or many Bunsen, not many, all Bunsen burners, which are actually used for boil water, speed lamps can not usually boil water. Speed lamps do not have that kind of energy output. They are just mid kore jole. They just have a very small, very weak flame. But Bunsen burners are run by pressurized gas. So Bunsen burners can have the ability. They have the amount of energy transfer rate that can enable us to boil the water. So every Bunsen burner comes with a regulator switch. You can actually increase or decrease the fierceness of the flame. So by controlling that, we have to achieve an equilibrium. That okay, fine. Whenever we have kept the Bunsen burner at this height and we have kept the knob at this position, the water is boiling. We can see that steam is gonna be coming out through this pipe, and the pressure between the two manometers are also exactly equal. We have to maintain all of this stuff and achieve this very critical condition. Do you understand my point? Water has to be boiling, steam has to be seen to come out, and the manometer levels should be same on both sides. We have to somehow reach to this exact sweet spot. And at that point, the level of the mercury in the thermometer is the steam point detecting level, or that is the level representing 100 degrees Celsius. We're going to give another mark on the thermometer over here, which means that in this case, we're going to give one mark right over here, and we're going to give another mark over here. And then we're going to take it out and measure how much is this. And using basic ruler, we're going to divide this whole gap in between into 100 equal pieces or 100 equal spaces. So if we can actually make it into 100 equal spaces, each space would represent 1 degree Celsius. If we divide the in between space into 50 equal spaces, then how much would be each gap? Someone tell me before I pick a person. If we divide this gap into 50 equal spaces, how much temperature would each gap represent?
2 degrees Celsius?
Kото?
2 degrees?
2 degrees Celsius, exactly. So whether you are going to be able to divide this space in between space into 100 spaces or 50 spaces is also dependent on how long your thermometer is. If you have a thermometer that is only let's say 2 inches tall, or let's say 3 inches tall, it is quite impossible to propose that we can actually divide this into 100 equal spaces, because those printed lines or those gradation lines will be very close to each other, will become very close to each other, right? বললাম বুঝতেছো কি বলতেছি?
Yes, sir.
So আমরা মোট কতগুলো ডিভিশন করতে পারবো সেটা একটা ফিজিক্যাল লিমিট আছে, and that limit is happens to be one of the primary limit of this thing is that how long was this test tube to start with. Any questions so far about the whole experiment and everything? Samira, তোমার question answer পাইছো? Hello.
Yes, sir.
Okay. So this whole process of marking the ice point and steam point on a thermometer, and then dividing the whole space in between in equal spaces, this whole process is what we call calibration. To use a device, we have to have calibration. A device is not usable unless it has calibration. For example, মনে করো হচ্ছে আমি তোমাকে একটা অ্যামিটার দিলাম, যে অ্যামিটারের ডায়ালে অ্যামিটার সবকিছু আছে কিন্তু ডায়ালে কোনো কিছু লেখা নাই. There are no gaps or there is no unit written. But whenever you connect the emitter to a certain circuit, you can see that the pointer actually moves around, which means the emitter works. But if you don't have the calibration behind that pin or behind that movement, that doesn't actually help. It doesn't actually work. So a device is only usable whenever it has a correct calibration. So এই calibration করাটা অনেক important. অনেক important. ঠিক আছে পোলাপান?
Yes, sir.
আচ্ছা, পোলাপান 1 মিনিট. উপর হয়ে পড়ে যাওয়ার মতো ভাব করতেছে, এরকম করতেছে. না আমি পাইতেছি না, ওর কি নিচে নামায় দাও. So this is called calibration, and calibration is a very important step for using a thermometer. So how can you use one of these thermometer to measure some length? Now to do that, how about, can I crop this picture? Well, maybe I can't, but I will use snipping tools. আচ্ছা, এটা পুরোটুকুই নেই, সমস্যা নেই. All right, I am using the horizontal version because for my screen orientation, it is easier for me to work with the horizontal version. Okay. এখন মনে করো আমরা এই থার্মোমিটার দিয়ে একটা টেম্পারেচার মেজার করব. Well, if the thermometer is calibrated, measuring the temperature out of the thermometer is actually quite simple, or actually quite easy. But let's say for reasons unknown, a thermometer that is not calibrated, but it has the 100 degrees Celsius mark, and we are provided with some information. Let's say the question gives us that the length from the very left edge all the way up to the 0 degrees Celsius is, let's say this is 2 centimeter, and the length from here all the way to the 100 degrees Celsius value, let's say this is 15 centimeter. And for an unknown temperature, means that we did these two mark and then we did not do the gradation marks or the in between lines, but rather what we did is that we put this object into an unknown temperature object, liquid or gas. We actually put it somewhere and we obtained another mark for that possible temperature where the mercury column, let's say, went up to this level. So they are also giving us this length. Let's say this length over here is what, let's say 7.8 centimeter. এই ভ্যালুগুলো মনে করো আমাদেরকে দেওয়া আছে। তোমরা বুঝতেছো কি করতেছি?
জি স্যার।
এই ভ্যালুগুলো আমাদেরকে দেওয়া আছে। সো এই ভ্যালুগুলোকে ইউজ করে আমাদেরকে বের করতে বলছে যে এই যেই লেভেলে আমাদের এই টেম্পারেচার, এই লেন্থটা আসছে, এই টেম্পারেচারটা কত, এটা বের করতে বলছে। এটা খুব কমন একটা প্রবলেম। এই প্রবলেমটা আমরা কিভাবে সলভ করি আমি সেই জিনিসটা তোমাদের দেখাচ্ছি। হ্যাভ আ লুক। ডেল্টা থিটা proportional to delta L. So I can write theta 1 minus theta 2 should be proportional to L1 minus L2. Similarly, I can also write, let's say, theta 1 minus theta 3 would be proportional to L1 minus L3 if we have another L. Similarly, theta 2 minus theta 3 should be proportional to L2 minus L3. I can write a lot of equations like this. The whole idea is that we have to use the same thing. And the beauty of proportionality is that if you want to convert this into an equation, let's say if I want to convert this into an equation, I can write that theta 1 minus theta 2 equals to a constant k into L1 minus L2. For the second equation, I can write theta 1 minus theta 3 equals to that same proportionality constant k multiplied by L1 minus L3. And same goes for the third one as well. If I now divide these two equations, what I'm gonna get? K and k will cross each other, and I can get an equation like this: theta 1 minus theta 2 divided by theta 1 minus theta 3 equals to L1 minus L2 divided by L1 minus L3. এই যে এই প্রপোর্শনালিটি থেকে কিভাবে এখানে আসলাম, এটা কি বোঝা যাচ্ছে সবার?
জি স্যার।
So basically,
কে কিভাবে ক্যান্সেল করছেন?
yes,
কে আর কে কিভাবে ক্যান্সেল করছেন?
because this is applicable for a single thermometer where the proportionality constant for any temperature change is proportional to the same relevant length, which means that proportionality constant has to be same for all of those values. Any temperature difference is proportional to the relevant length change. So that proportionality constant is a constant for this thermometer. It's an inherent property of that thermometer.
আচ্ছা।
বুঝা গেছে?
Yes, sir.
All right. So AG equation I build up. This equation was built up in a very gross form. So I'm gonna actually write up this equation in a slightly different way. So have a look. I'm just লিখতেছি আগে, তোমরা খেয়াল করো। Theta, which is the unknown temperature, minus 0 degrees Celsius divided by 100 minus 0 degrees Celsius equals to L theta minus L0 divided by L100. Sorry, 100 is 1 degrees. L100 minus L0. এই ইকুয়েশনটা ঠিক আছে না? থেটার জন্য L theta, 0 এর জন্য L0, 100 এর জন্য L100, 0 এর জন্য L0. You might wonder, এটাই ইউজ করতে হবে? এর আনসার হচ্ছে না, এটাই ইউজ করতে হবে এমন কথা নেই, বাট এটা ইউজ করলে কিছু অ্যাডভান্টেজ পাওয়া যায়। অ্যাডভান্টেজগুলো কিরকম আমি দেখাচ্ছি। সো এখানে যেহেতু আমি 0 0 সাবট্রাক্ট করলাম, সো আলটিমেটলি এখানে আমার কি আসবে? থেটা এভাবে 100 আসবে না? আর এখানে আসবে কি এল থিটা ভ্যালু এখান থেকে দেখে বসাই, ফিগারটা থেকে দেখে বসাও। এখানে আমাদের আননোন টেম্পারেচার জন্য রিলেভেন্ট লেন্থ ছিল 7.8. সো আই এম গোনা প্লেস 7.8 ওভার হিয়ার। 0 ডিগ্রি সেলসিয়াসের জন্য লেন্থ ছিল কত? 2 সেন্টিমিটার। আই এম গোনা প্লেস 2 ওভার হিয়ার। 100 এর জন্য লেন্থ ছিল কত? 15। আর 100 আর 0 এর জন্য লেন্থ ছিল হচ্ছে 2. সো আলটিমেটলি হোয়াট ইউ আর গেটিং, থিটা ইকুয়ালস টু দিস হোল থিং মাল্টিপ্লাইড বাই 100. এটা হিসাব করে দেখো তো কত আসে? সামওয়ান টেল মি। 5.8 divided by 13. 53.8. না,
0.44 মানে 45
ইন্টু 100 আছে, তার মানে হচ্ছে 44.6 ডিগ্রি সেলসিয়াস, ঠিক না?
ইয়েস স্যার
সো এটা হচ্ছে ক্যালকুলেশন করার মেথড, এটা হচ্ছে ক্যালকুলেশন করার ট্রু ওয়ে। এখন তোমাদের বইতে এই টেম্পারেচার রিলেটেড ক্যালকুলেশনগুলো করার একটা মেথড দেওয়া আছে। সেই মেথডটা হচ্ছে এরকম, খেয়াল করো, মেথডটা হচ্ছে এরকম, থিটা ইকুয়ালস টু L theta minus L0 divided by L100 minus L0 into 100. এই ফর্মুলাটা তোমাদের বইতে আছে। This formula is okay when we have access to this information exclusively. But what if the question was not set in this way? What if the question was not set in this way? Let me show you an example for this. মনে করো এটা একটা থার্মোমিটার, is there a way I can crop this? Apparently no. Okay, I'm going to create a cropped version, doesn't matter. মনে করো কোন একটা কোশ্চেন আমাদের এই লাইনগুলি দেওয়া আছে, খেয়াল করো, it is given and the unknown length, let's say, which goes up to here. This is that unknown length is given as the question হচ্ছে এই টেম্পারেচারটা কত। এখন আমরা কোন ইকুয়েশন ইউজ করব? এখন কিন্তু আমাদের টার্মিনাল ভ্যালুগুলো কত, 0 এবং 100 নাই। The values, terminal values are not 0 and 100 anymore. This the terminal value over here is -10, that the higher value over here is 120. So if these are the values that are given, can we use this equation? Can we use this equation?
Yes.
No, because
sir.
this equation was exclusive for 100 length for the 100 degrees Celsius and length for 0 degrees Celsius. This equation are exclusive for that. We cannot use this equation because in this new figure that I've drawn over here, we don't even have the length for 0 degree or length for 100 degree. What are the lengths we have? We have the length for -10 degree, and then we have the length for 120 degree. Am I correct or not? সো এটার জন্য আমি স্টুডেন্টদেরকে বইয়ের ওই ফরম্যাটটা শিখাই না। আমি স্টুডেন্টদেরকে যে জিনিসটা বুঝাই সবসময় সেটা হচ্ছে তোমরা এই ফরম্যাটটা শিখবা, unknown temperature theta minus lower temperature divided by higher temperature minus lower temperature. So by H and L I'm representing low and high equals to L theta minus L of lower and then length of high minus length of lower. এই কোশ্চেনটা বুঝতেছো? বলবান দেখো তো বুঝা যাচ্ছে কিনা? I hope so. So now I'm going to place these values. Theta minus -10 divided by 120 minus -10 equals to 7.3 minus 2.1 divided by 14.8 minus 2.1. এখান থেকে আসবে হচ্ছে theta plus 10 equals to something into 130. Therefore, theta equals to হিসাব করা কত আসে এটা 7.3 minus 2.1 মানে হচ্ছে 5.2 divided by 12.7. Minus 10. 43.2. আমি কিন্তু আবার এটাকে কিন্তু ওই পাশে নিয়ে একবার সাবট্রাক্ট করছি দেখছো এটা কিন্তু থিটা প্লাস 10 এখানে কত শুধু থিটা মানে এটা ক্যালকুলেট করে যা আসবে সেখান থেকে কিন্তু আবার 10 আবার সাবট্রাক্ট করতে হবে খেয়াল করো এই ভ্যালুটা আসছে কিনা সবার দেখো নিজে ক্যালকুলেট করে দেখো এই ভ্যালুটা মিলছে কিনা মিলছে
জি স্যার।
আচ্ছা মিলে নাই কেউ আছো No, I guess. So do you understand why I prefer this version? This is a more generic version of the formula. Whereas that formula that was given in your book, you can turn up your book, is exclusively applicable for zeros and hundreds. I like this one better. This one works better, and this one is more reliable in my opinion because you are not going to be trapped anywhere. Whatever the values are given, you can work with it. আচ্ছা আরেক টাইপের কোশ্চেন যেটা হতে পারে এমসিকিউ কোশ্চেন একটা এক্সাম্পল দেখাই
স্যার বুকলেট কি রেডি হয়েছে?
What is this? এটা থার্ড এন দিয়ে শুরু হয়েছে কেন কিছুতে আচ্ছা Where is বুকটা রেডি হয়েছে কিনা একদম ক্লাসের শুরুতে বলছিলাম আচ্ছা এখানে একটা জিনিস খেয়াল করো এই একটা কোশ্চেন আমি দিস আউট বুকটা রেডি হয় নাই কারণ নোটস বানানো হয় না নোটস বানাবো তারপর বুকটা দিব তোমাদের একটু সময় লাগবে ইন দ্য মিনটাইম তোমাদের কিছু কয়েকদিন পরে তোমাদের পুরো নিউটন ম্যাগনেটিক্সের ক্লাস টেস্ট পেপারগুলো ট্রান্সফার করে দিব তোমরা সেগুলো প্যানেলের সুপারভিশনে পুরো পরীক্ষা দিবা তারপর তোমাদেরকে কোপ দেওয়া হবে সো এই কোশ্চেনে আমরা একটু দেখি it is also a very similar question but you can see over here other than giving the length of individual minus 10 degrees Celsius and the whole thing they have given the length from here to here do you see this what I want you to understand that this length actually represents L theta minus L minus 10 ঠিক না দেখো তো this is the delta L already we have the delta L over here or I can write in another way let's say delta theta is proportional to delta L which means theta minus theta minus 10 divided by 110 minus 10 এখন একটা জিনিস খেয়াল করো এই থিটা আর মাইনাস 10 এই দুটো টেম্পারেচারের মাঝখানে লেন্থ কত থার্মোমিটার দেখো হ্যাভ এ লুক এট দ্য থার্মোমিটার what is the length variation this is the unknown this is theta so এই থিটা টেম্পারেচার এবং মাইনাস 10 এর মধ্যে লেন্থ ডিফারেন্স কত 15 না বলুন দেখতেছো the difference of length between because I was supposed to write delta L over here but that delta L is directly given so I'm going to only write 15 over here I don't have to subtract anything if it so happened that I was given, if it so happened that I was given this length individually and this length individually as well, like the earlier case, like the case over here, have a look, one length and then the other length, the two lengths are given individually, then I had to go for the actual subtraction. But in this case, the difference itself is given, which means I can directly place the difference right over here. This here is 15 and here is 25. And now try to solve this thing for theta. এই কোশ্চেনটা থিটার জন্য সলভ করো, কত হয় দেখো। বুঝা গেছে কিনা দেখো পোলাপান। বুঝা না গেলে কোশ্চেন বলো। হ্যালো, এই কোশ্চেন, এই সলিউশনটা কি সবার বুঝা গেছে? It's important that you understand this thing. It's important that you understand the difference between these two figures. Here, individual lengths from a certain reference point. In this case, the reference point was the very left edge of the thermometer. সবগুলো লেংথ এখান থেকে একটা, এখান থেকে একটা, এখান থেকে একটা, তিনটা লেংথ এই একই পয়েন্ট থেকে দেওয়া ছিল। That's how we had to use this information. We could place all the individual values over right over here. L theta, এটা এটা এগুলো সবগুলো ভ্যালু ইন্ডিভিজুয়ালি আমরা এখানে বসাতে পারছি। বাট যদি আমাদের সরাসরি ডিসটেন্স ডিফারেন্সটাই দেওয়া থাকে, which is shown over here, then there is no point of doing the subtraction over here because the difference is already given. So 15/25 comes in readily. So question এরকম হতে পারে, question এরকমও হতে পারে। Questions, kids. I'm going to zoom out a bit so that you can see these two figures side by side and be able to understand the difference. Any questions so far? Hello, hello. Microphone testing 1 2 3 4. Nope. Acha. Using the exact same mechanism, can we try to calculate number 10? I'm going to put the question in the whiteboard for your sim because you don't have this worksheet. Please attempt this question and get the answer. এটা একটু ট্রাই করো সবাই। Write the answer. Do not detail the answer. Write the answer in personal chat to me. Send this answer as a direct message in the Zoom chat window to me. Everyone. There are 7 students in the chat. I want to see you work. Okay, I got one response from one of your classmates. That student responded to be B. I'd like to see more responses. Second response, 6 more to go. I can see the degrees are taking out time to solve this problem. Please do. And do solve this problem. You are allowed to be mistaken, which is perfectly all right. That's the whole point of doing classes. This is not a test. This is just a classwork. So if you're mistaken, no big deal. I'll pick up the discussion of this class in the next class. That is on next Tuesday. Today, I actually planned today to discuss for a shift of the Friday timing, which I couldn't because I jumped into the thermal chapter. On our next class, we'll definitely discuss about the change of timing for the Friday class if possible. Possible means if every one of you can accommodate a new timing, can accommodate, not that you have to, but I would like your help in this manner. And also if you have any question from the density pressure chapter or the composite, so I'm going to put these two chapters as your homework. Density pressure paper 2 first, you attempt all of the problems as best as you can, and if you're done with this, jump into the total composite, so not total composite, the intermediate composite, and try as many problems as you can. Make sure you finish the density pressure paper 2, and the composite is optional. If you can do it, I am eternally grateful to your service. So yeah, see you all on Tuesday. Allah Hafiz. Thank you.